This is Boris Shafran of Evonik Jayhawk Fine Chemicals Corporation, welcoming you to Part 2 of our joint webinar series with Dixie Chemical Company, where we examine the performance properties of epoxy syntactic foams in service. In today's presentation, as we also touched upon in Part 1 of our webinar series, our focus is on the deep water exploration of oil and gas reserves. And in this type of an application, where ocean depths are greater, where longer lengths of rigid pipe are required, the reliance upon syntactic foam as an insulating layer for these pipes to ensure the transport efficiency of the crude to the surface becomes more vitally important. What we found in Part 1 is that the thermal curatives used with epoxy resins in this application can have a profound effect on thermal properties and mechanical properties of these syntactic foams. What we have prepared for you today is a review of a host of different properties of these foams, showing you how they relate to one another and showing you how they can be greatly influenced by the selection and, in this case, the blending of different thermal curatives for these formulations. So we invite you to prepare your comments and questions. As we go through the presentation today, we'll take about 30 minutes to do so, and we'll conclude with a Q&A session and panel discussion. So thank you very much for your attention thus far, and let's continue with the discussion. So let's take a look at the overall goals of the research study, where we've been and where we want to go today and in future. In Part 1, what we focused on is just what the potential would be for combining different thermal curatives, in this particular case monoanhydrides and dianhydrides, and what influence they would have on the properties of the epoxy syntactic foams. And we started to find some very interesting results, particularly with regards to glass transition temperature and compressor strength. With that as the foundation, the Part 2, which will be the subject of today's discussion, is a little bit wider look with a series of different properties to really better classify the performance and to validate what it is that we saw in Part 1. So this will be presented to you today. What we like to look at going forward is, once we determine what this more optimal mix is then to fabricate some parts and to do some deep sea installations and some monitoring to further show that what we're seeing in the lab translates into in-service performance in the field. So that will be coming in a future study. So this is the full review of Part 1 with regards to the conclusions that we found. The first thing, obviously, from a deep sea exploration standpoint, is that syntactic foams represent a key technology and play a key role here, specifically with the regards of transport efficiency of the crude reserves. Epoxy syntactic foams, which have been utilized for some time, it's required that we kind of take a fresh look at them with regards to how they're formulated. We can make some slight changes and create some very different results, as we have begun to discover. From our standpoint, the use of thermal curatives is one of the strong levers to play this role, to show how the in-service properties can be altered through simple changes in your formulation. These curative blends, as you start to look at more of them and how they're blended together and which ratios, really start to open up the idea of maybe tailoring properties of these foams, especially as you're looking at more extreme and more harsh environments for oil and gas exploration. we identified that a modeling study is necessary to further predict the performance so that there is maybe not an elimination, but certainly a reduction of constant trial and error to try to understand how to improve the performance of your formulation. And we do have some news to share with you today regarding modeling studies and modeling tools that are now available to you. So this is what it really boils down to. How do you take a thermal curative either on its own or in a blended system as we are proposing? How do you take that and apply that to an ordinary, traditional epoxy syntactic foam formulation, one that's well defined in terms of its properties and its potential? How do you take that and transform it into an extraordinary material that has newfound levels of performance? And in this case, we're talking about thermal, mechanical behavior, but for that matter also processing, to ensure that you're making an optimal composite from a viscosity standpoint, from a void reduction, from a microballoon fracture reduction standpoint. All of these things we find are related to one another. We believe we have found the various levers, and this is what we want to present to you today. What then are these levers, these key drivers for syntactic foam performance? These are the ones that we've taken a look at. First one is glass transition temperature, which clearly is related to greater heat resistance and dimensional stability of the foam, particularly at greater ocean depths. Thermal conductivity, the insulative quality of these foams, inherently so because of the fact that they contain these microballoons, these air-filled microballoons or gas-filled microballoons. The insulative quality of these foams is going to address the heat transfer between the crude oil, the rigid pipe wall, the foam itself, and then into the surrounding ocean environment. So the transport efficiency of the crude oil is imperative. You can also address paraffin formation by controlling thermal conductivity of the formulation. Density is inherent to this type of foam system. It's a buoyant system because of the microballoons, which include air or gas. So these materials are inherently buoyant and lightweight, but can the density be improved, especially when you're looking at these long lengths of pipe? Compressor strength is something that clearly has a correlation with hydrostatic crush strength, and here we found a very interesting improvement in performance, something that would certainly serve these deeper ocean environments where the stresses are much greater. And overall water absorption, how well can this composite material resist the ingress of water, either on its own or via crack formation or any type of damage that occurs to the material? How well can it stand up? So this speaks to its integrity and its overall service life. Here's the testing program which we put together to try to understand how the curative blend will affect these properties, these drivers. And these formulations carry over slightly from part one of our presentation. Here we go into greater depth where we're looking at a specific ladder between one monoanhydride and one dianhydride. We selected natick methyl anhydride and BTDA, which is benzophenone tetracarboxylic dianhydride. The NMA is a liquid, the BTDA is a solid. So that speaks to some of the processing issues that I had referenced previously, and I'll show you how those work going forward. We also included, as a standard, 20% loading of glass microballoons. We utilized the standard EPON 826 resin as our basis. And our cure schedule is 4 hours at 220 degrees C. We have essentially created a ladder from 0 to 100% BTDA content. We have included BDMA as an accelerator, and the foam composites were produced in these loaf pans, as you see to the right here. Pretty typical of how they look. You see a mild surface crack, but beneath that there is plenty of material which we utilized to prepare our specimens. Now that you've seen the formulations, we'd like to present to you the data from the various properties that we measured. Everything is covered here except for water absorption, which we had to delay until future testing round. But what we have here is, and it's a little bit of a busy slide, but I wanted to present everything to you here so that you could see the relationship of one property to another. Each property is shown as a function of curative ratio, and we start with the upper left corner, which is glass transition temperature. And as you see here, this is fairly predictable performance. We've got increasing cross-linking density afforded by the increasing amount of BTDA. So you've got a very nice increase in glass transition, which leads to improved heat resistance. And all of this can be put to very good use when you're looking at deep water applications. The only drawback is that now the foam composite has become more rigid. You've introduced brittleness. So the full benefit of the BTDA in all likelihood needs to be pulled back to a reasonable compromise so that you've got a material with some good integrity and also gives you good heat resistance. Very similar performance can be seen in the graph of compressor strength, where you're basically you're tracking the same behavior. You've got increasing cross-linking density, you're able to withstand greater stress, and as a result, the increasing dianhydride content is affording you higher levels of strength. This translates or correlates with hydrostatic pressure, hydrostatic crush strength. So once again, addresses the environment of deeper ocean depths. This clearly works in your favor. When we look at thermal conductivity to the upper right and density below it, this is where the results start to become a little bit peculiar and not so simple to explain. In the case of thermal conductivity, there's an actual increase, a mild increase, and this somehow implies that the insulative quality is not as good. It's a little bit hard to understand. And now when you look at the density as well, you see it goes through an optimal peak and then it decreases, and also seems quite odd. So with regards to those two properties, we feel there's something suspect here, and we're going to take a look at microballoon fracture and integrity, because if those if those qualities are off, then those should clearly impact the two things that we've seen here. So we have some additional data which we will present to support our observations there. The one thing which is not covered here is what is the influence on processing of these blends. The BTDA, as we described, is a solid, the NMA is a liquid. So to put together combinations of the two can result in some type of a nice mixture, which can then be introduced into your resin and your fillers and mix well and give you good homogeneity of the finished composite. In order to get that, we've come up with a recommended blend of 45 to 55, and as you see on the various graphs, that amount affords you a nice kind of a compromise figure in each sense, where you gain an improvement in properties, and so you can address in-service performance as well as processing performance, in the plant environment. These concepts are further emphasized here in this kind of quick assessment of where we are. So we have so far shown that these epoxy syntactic foams can be designed with very nice improvements in these properties, and purely due to how you put together your curative blend, as well as the selection of the individual curatives themselves. So here is where some fine-tuning can truly optimize your mix design. But what about this issue regarding microballoon integrity? So what has happened? We suspect that this is the case, that there has been fracture, but what has actually happened? Let's take a look at this in greater detail so that we can relate the results to our expectations. This schematic of microballoon fracture will help to explain what we believe is going on. So what happens when this little microballoon breaks within the composite material? So on the left you've got an intact balloon. It's got a typical density as shown. It's filled with air or gas. As it's introduced into the composite material, it's going to address density, buoyancy, all the things that you want. But if it breaks, what happens? So now you've got the pieces, the shards of the balloon within the composite material instead. So because it's collapsed, because you've lost the air within the intact balloon, now you've got a tremendous decrease in volume. And what has taken up the space that the microballoon should have occupied? Additional resin. So your density has essentially increased tenfold. You've lost the volume afforded by the intact microballoon. And assuming that there are no voids, you have a much denser material because of the amount of binder in a given volume. So this clearly explains what we've seen in the previous slides, and it also brings into question, if we have experienced microballoon failure, how much better could those other properties have been, specifically glass transition and compressor strength? Here are some additional data to support the same type of behavior which we suspect. In the background you see a nice micrograph of one of the samples. You see a lot of broken microballoons. Some are very much intact, you see them, but on the left you see a broken one. On the right you see one which is cut in half. That could have been just by maybe the preparation of the sample, but you see a lot of shards throughout the composite. So if you do some basic mathematical analysis, and if anybody's interested in this, I'd be happy to share it at a later time, you can look at what the impact is of syntactic foam density as a function of fractured microballoons. And you see a significant behavior here, a significant result. So this could very well have played into what we had shown you previously with that peak behavior in density as a function of curative blend. This is the previous data set, which we have now amended with data which we believe tracks the amount of fractured microballoons in each instance. And we have determined this based upon the relationship that we showed in the previous slide. So for each data set, the original data appears in purple, and the microballoon data appears in orange, as measured by the axis to the right on each graph. So now some additional conclusions can be drawn and some questions can be raised. With regards to glass transition temperature, we do not expect any effects here because that should simply be inherent to the polymer behavior and should be independent of any fillers which are in the system. So we believe the data as originally generated there is as stands. The compressor strength data to the lower left could certainly be influenced. Intact microspheres, perfectly round spheres, in the composite material should be able to withstand greater loading and greater stress before fracture. So perhaps the slope of the compressive strength line could have been changed. You see, in the mid region is where we experienced some greater microballoon fracture. So it's certainly possible that the slope could have been different and in our favor, so to speak. The thermal conductivity data now starts to make a little bit of sense because there is a greater degree of fracture in the middle section of data. If that were not the case, and if that line was relatively flat, we believe that the thermal conductivity line would be similarly flat and of a different slope, more level slope. Could there be more uniform thermal conductivity with fully intact spheres? It certainly stands to reason. So the same can be said of the density. In the middle of the graph, you see where the microballoon fracture was the greatest, and as a result, the density tracks right with it. So that speaks to the previous discussion about what happens when a microballoon breaks. So that tracks fairly well there. So how do we improve this? How do we ensure the survival of the microballoons in the mixed composite and the cured syntactic foam? So now we've got another element to consider here. Is there an optimal loading of microballoons to accomplish this? We went with 20%. Perhaps there's a different amount which would produce more intact microballoon content and drive the properties to even greater extremes. These things are all possible. The other issue is the processing standpoint in terms of how the spherical fillers will improve the mixed viscosity of the formulated material. So we've got an added variable now of microballoon integrity and how that needs to be addressed going forward. So the future needs list has evidently grown to include a couple of other issues here. Some additional data, which certainly would be useful for reproducibility and to minimize the variation in what we have seen, although we have demonstrated some very clear trends with regards to the influence of the curative blend on the properties that have been measured. Processing techniques now come strongly into play because we experienced some microballoon fracturing and as a result some inconsistent property measurement. So examining lower loading levels, different types of mixing techniques, perhaps different types of microballoons with different degrees of toughness, if you will, to prevent and to safeguard against fracture. These are things that we would like to take a closer look at. As we had mentioned previously, fabricated foams placed in service would also be important to understand and to validate what it is that we've seen here today. Modeling systems, which we have spoken about in the past, which would help to fast track the performance of these systems with regards to design. And here we do have some news which we can report to you today. NYU's Tandon School of Engineering in Brooklyn, New York has recently introduced this new syntactic foam design tool. It is an open access tool. It's available at designsyntactic.com. What it does is it starts with a series of preloaded data sets based on characteristics of different foams of different resin types. And it allows you to visually see the dependence of one property upon another. There are also contains the ability to do contour graphs of same, so you can start to zero in on the proper mix design and the proper formulation that you may need for your given application. So this is relatively new. The other thing that can be done is that if you have a specific foam formulation, you can input some data, a couple of different parameters, and then it will generate the same type of comparative data for you and save you some steps. So it's an educational tool. It helps you understand the difference and the relationship between the properties, as we have shown you today. And it also helps you going forward as a design tool to reduce your trial and error when you put your syntactic foam formulations together. I'd like to conclude with the following remarks. First of all, I think we've demonstrated quite clearly that different curative blends, specifically BTDA and NMA, can really show great promise. If you put them together in different ratios, you can impact some of those performance properties quite markedly. So that's worth considering going forward in terms of what the right blend is, and do you need to tailor the blend in order to suit the particular process requirements or property, whatever is more important to you. Now you see the various levers in action and how they work in regard to one another. The other thing we've uncovered, which certainly isn't new, but from our standpoint, we just have found that the microballoon fracture which we have experienced can really be an impediment to realizing the full potential of these systems. So if you want to drive compressive strength and now you've got a certain percentage of fractured microballoons that you have to deal with, you're not going to get to where you want to go. So from a formulation standpoint, you may have designed something optimally, but then if you translate that into a processing environment, you may have lost everything by virtue of the fact that you're sacrificing the balloon integrity to mix the materials together. So simple concept, but has a large impact and a large consequence. Proof of concept is still required here. We're doing everything on a developmental basis, on a lab basis. This stuff has to be transitioned into fabricated parts that are put in service where the results can truly be validated. But so far, everything is moving in a very positive direction. Lastly, the new modeling systems which are starting to emerge are going to help a lot to address the challenges of putting these formulations together, work to minimize the trial and error side, help to better understand what type of mix design you need for a given requirement. We're just at the start of that, but those are now going to help us in a significant way. On behalf of Dixie Chemical, we at Evonik would also like to acknowledge and give special thanks to the following colleagues who have helped us tremendously understand the behavior of these foams and guide their further development. Gary Gladitz at Dixie, Brian Pillay and his staff at UAB, and Nikhil Gupta at NYU Tandon have all been extremely helpful, and we recognize them here. And finally, I'd like to thank you, the audience. On behalf of Dixie and Evonik, thank you very much for staying with us. We started off with a certain premise. We went in a couple different directions. I think we kind of came back at the end and tried to summarize as best we could where we've been with our program and where it is that we wish to go. So the complexity of these systems is now, I think, being brought to the forefront in terms of how the behavior can be influenced. Curative selection, curative blending clearly plays a role. Processing safeguards, understanding of microballoon selection, loading, safeguarding fracture, these things all come into play with regards to the end use, the performance of the syntactic foams in service. So have we demonstrated that the envelope can be pushed on their performance characteristics? The answer is yes. Have we uncovered some pitfalls along the way that you have to look out for in order to get to this high level of performance? Yes, we have. We intend to address these further as we go to part 3 of this webinar series, which we hope to present to you in the very near future. So thank you once again for your attendance, and have all of you have a great day.
Hello, everyone. My name is Jane Arlauskas. I'll be the moderator for our panel discussion. And on the panel today, we have Allison Considine, Jeff Dimmitt, and Boris Shafran. The first question we have today is, what are the defining properties for epoxy syntactic foams?
Hi, this is Boris. I'll take that one. Thanks, Jane. As we covered in the discussion, a couple of things came to light, and these were featured in part 1, and now we're able to generate some quantitative data in part 2. But the properties that we're talking about really begins with glass transition temperature, which is the first thing we really need in order to define and understand the behavior of the foam as it is exposed to hotter versions of crude oil and at deeper depths. So it's necessary to understand the heat resistance of these foams, and glass transition is going to give you that first indicator. The second one, which we presented today, is compressor strength, and that can be interpreted a number of different ways. A straight compressor strength, as you saw in the data, we got a very nice progression as we change the blend of the curative, and that will translate directly into hydrostatic crush strength, or at least you can make a correlation as such, so that as you're contemplating the use of and trying to simulate the performance of these epoxy syntactic foams at deeper ocean depths, you can gain an appreciation for a higher compressor strength, being able to provide you with a better hydrostatic resistance at the greater ocean depths. So those are the two that are the most important. Those are the two that we've really been able to change and modify with the introduction of blends of dienhydrides and monoanhydrides. The density data, which also is important in terms of more from a processing and a handling standpoint, that the material is very lightweight, easy for fabricators to handle and use, and thermal conductivity, which we showed you also. We don't expect any great variance, but those, of course, are equally important properties for syntactic foam. Hey, Jeff or Allison, is there anything that you'd like to add to that?
No, I think you covered it pretty completely, Boris. I mean, just to emphasize, yeah, you need a material that's cross-linked extensively enough to allow it to operate or to survive under the increased temperatures that the material will experience in deep ocean downhole temperature ranges. It's got to be able to support the column of water that's sitting over it, and then yeah, I think density also as well, simply because you need to be able to help a little bit with the buoyancy of these materials so that they aren't adding tremendous weight to the overall mass of the system that's being supported.
Okay, thank you, Jeff. The next question is, what role do dienhydrides and monoanhydrides play in tailoring performance?
Thanks, Jane. Oh, go ahead, please, Jeff. Take it.
I was going to say, I'll start with that one. I mean, the role of the dienhydride and the monoanhydride goes to the extent of cross-linking of the epoxy resin itself. As the data showed, you can really affect the properties of the finished product by the ratio of monoanhydride to dienhydride. The main effect of using BTDA as a thermal curative for these systems is that it's tetrafunctional as opposed to difunctional in the monoanhydride, which imparts much greater cross-linking density, and therefore really driving up the properties, the thermal properties and compressive properties of the material. The monoanhydride as a bifunctional or difunctional cross-linker imparts its own properties. It doesn't cross-link as extensively as the dienhydride does, but it does serve a very useful purpose in helping integrate the dienhydride into the epoxy resin itself during formulation and curing. Anything to follow up with, Boris?
Sure. Yeah. Thanks, Jeff. Well, the one thing is that if for the attendees, if you were present for the Part 1 webinar a while back when we just kind of introduced the concepts of these, here we were able to really show you quantitatively what this effect is. And as you change the ratio of the dienhydrate to monoanhydride, now you can see there's a very marked effect that it brings and actually affords you the ability to choose what it is you want. So you can really start to understand how you can kind of tailor-make and design these foams by virtue of the formulation, specifically the curative blend, to give you exactly what you're looking for. If the foam that you're manufacturing is too rigid for your requirements, now you can gain an understanding of how to dial that back. And accordingly, the same thing with glass transition. The main thing we wanted to illustrate today is that how that's possible, and I hope that the participants have seen that and gain an understanding of that today.
Okay, thank you, Boris. The next question we have here is, what is the importance of microballoon integrity, and how do you safeguard this?
I'll take a shot at that, Jeff, and then if you'd like to offer some comments. But we've found, I mean, this obviously, and we covered it in the webinar today, was not something that we intended to focus on, but we had to because of the results that were obtained. And it's my firm belief now, after having these tests performed, is that fabricators or companies, when they're putting together these syntactic foam formulations, are quite focused on efficient mixing and curing of the foam. But now we've got this other variable here, which seems pretty straightforward, but now we uncovered it in greater detail in terms of, hey, what happens if you're a bit too aggressive and you mix too well, or let's call it overmixing. Now you're going to introduce the concept of fractured microballoons, which, and as we showed to you in the data today, the tremendous impact it has on all of the properties, some of which we were able to pin this to, others which were a little bit more food for thought. But you want to put together a very dense epoxy syntactic foam matrix, you choose your ingredients, you do your mixing, and now you've got this consequences that, hey, maybe what I've produced is actually not giving you optimal properties because we've encountered breakage during the mixing process. So it is extremely important, as we have now demonstrated, and I think it actually held back some of the potential of some of the properties that we measured. We probably could have done that much better. So this may be common sense to people, this may be well known to people in the art, but now we're going to take a more careful look at mixing and processing techniques. The importance of blending some of the liquid and curative components is obviously extremely important and requires a high degree of shear. The introduction and the blending of the microspheres requires some type of guarded, more careful, more gentle mixing so that, yes, the balloons are mixed, they are wetted, they're integrated, you have a homogeneous matrix, but those balloons are intact so that at the end of the day, when you've created the final composite, you're going to get the properties that you're looking for to the greatest degree necessary. Jeff, does that pretty much stand with what you're thinking?
Yeah, it does, and I think it was important that we had to move to microscopy to try to understand what was going on with these foams and why the properties we were seeing didn't line up with what we expected to see based on knowledge going into the test. I think it showed taught us a lot about how these balloons have to be integrated into the system. Like you said, high shear for getting the resin ready and then moving to a really low shear, almost kneading system to fold the balloons in and distribute them and disperse them adequately through the resin without breaking any of them.
Okay, thank you, Jeff. Our next question, is there a means to model formulation performance before deciding on raw material selection and processing parameters?
Great, thanks, Jane. Yeah, I'll start with that. And is there a means? Yes. And are they starting to emerge, different types and different models and different means to measure? The answer is yes. And we gave you a brief introduction to the work that's going on down at NYU Tandon where Professor Gupta, Nikhil Gupta, has now put together such a model on, and we showed you the portal, which you can take a look at and start to gain an understanding of how the different variables affect the properties of the syntactic foam, and allowing you to kind of shortcut through your own personal trial and error and put together a foam and understand the the bill of materials which is required for that. So the NYU Tandon model is one of the first, and the one that has open access to allow you to at least start to understand the differences. Others are starting to come on board as well, and I'm sure there will be more, and we will take a look at that as we put together our data, which would be part 3 of this study. The other thing which we're taking a look at, and in terms of modeling, is to do some simulation. And this is something that we're talking about with some third parties in terms of putting together a fabricated part, which can then be put into service with various monitoring devices so that we can really understand how the foam performs in service. Jeff, would you like to also talk a little bit about this modeling program that we're contemplating?
Well, I think what we've looked at so far looks promising. I'm going to be very intrigued to see the results of what it predicts versus the part performance once we get to the modeling, or once we get to the actual application part of the project here during 2018. But the data I've seen to date says this program looks pretty powerful. I think it's going to be a useful tool for the industry.
Yeah, the third party that we've identified has already given us an idea of the size of the part and the testing program that they have in mind. So this will be a substantial part, and give us a reasonably good simulation. So that's something that we'd like to present to the participants as part of a part 3 of the webinar series, where we give you some more real-time data. So that should provide everybody with some better understanding, and as well as and everyone is welcome to take a look at the online, the open access model too. Just to you can start to gain an appreciation whether you use the data sets that are already part of the data set, or you can even plug in some of your own if you have that much specific information, and start to gain an understanding of the various effects that the properties have on the end foam. So this is kind of the evolution of our work, and we hope to feature this more in part 3 sometime during 2018.
Okay, great. Thank you, Boris. What type of foam would you recommend for aerial firefighting?
I don't know. That's not an application for syntactic foams that I'm aware of, Jane.
Okay.
I don't know. We just got that question from one of the participants. I don't know that we have an exact match with that. Honestly, what we'd like to do is kind of take that back, and maybe we can address that offline. It seems to me that would be something that wouldn't relate exactly to what it is that we're presenting today in terms of an insulating layer for a pipe. But we'll certainly take a look at that, and if it's okay with that person who asked the question, we'd like to take that offline and answer it at a later time. So appreciate your patience on that. And actually, anybody who has additional questions, whether you have them ready today or would like to cover them at some point in the future, you're welcome to submit them. We've already received a series of questions from our Part 1 webinar that ran just a few weeks ago, and we welcome any of the participants, whether a part of the live or the on-demand portion, to submit their questions for further consideration. But we'll take that one back and get you an answer later on, if that's okay. Okay,
great. And we have, how do these properties translate into in-service performance?
Well, I think that's kind of a real good kind of a summary question, and that's what we have been grappling with as we go further into this study. The first part of the study was really just to identify whether or not we could impact any change, and now we have found that we can. So clearly we can affect in-service performance. the open question that remains is what we have measured in the lab quantitatively. How is that going to translate into an in-service part? So we would like to use the next phase to really validate what it is that we've done, but so far we definitely have tripped onto something novel, and I hope that the participants appreciate that, and we'll be able to report on that in greater detail sometime during 2018. Jeff, would you like to add anything just to close out?
Yeah, no, I agree. I agree completely. I mean, we've shown that you can really tailor the performance of the finished syntactic foam by the ratio of monoanhydride to dianhydride to allow you to really dial in the properties you need for the specific application. I think that is like just want to echo what you said, which is that is really, I think, a novel finding, novel observation that I think is going to lend a lot of value as we go forward with this overall project.
Good deal.
Okay, thank you, Jeff. And I want to thank everyone for joining us today for improving the performance of epoxy syntactic foams, and thank our panelists, and also wish everyone a very joyous and happy holiday season. Thanks again. Enjoy the rest of your day.